basically, I want to cover three things, which are probably more familiar to statisticians. Here, one is here's a pointer. One is interpolation is something like a bias-variance trade-off, but we can go deeper, not only on the rate. We can go to the multiplicative constant. That may offer something different. And sparsity is something popular for many years in statistics. So how we do that in deep learning, and also the last one is optimality here. There are many ways of defining optimality. Here I'm trying to introduce some optimality fit into that teacher-student framework. Okay, I will start from a bit like a current state of art in deep learning. So to me, the most interesting part of deep learning phenomenon is that we already know that the landscape of the loss for neural network is highly non-convex, but we just apply the SGD or some variance. We can easily find out some like local or global optimal that can generalize well. Sometimes statisticians probably care more on this generalization. So of course there are three different ways of study the deep learning. One is about the approximation theory. It starts from very early, the universal approximation theory, to the more recent result that you can construct some functions that can only learn by deep neural networks, but not the shallow ones. Okay, and also optimization is also well studied. You say the sharp minimal versus flat minimal, and also how gradient evolve as iteration, and how these iterations go from one local optimal to another, some local geometry result as well. And the last one is about generalization. Basically, you can calculate the generalization error bounds based on the classical random complexity or some more modern complexity measure adapted to the neural network. And we also have some recent interesting results to make connection between the generalization and the over-parameterization. Okay? To me, I've learned this a lot from the talks here. And one missing piece, I think, that we probably can do something more systematically from statistics. Of course, statistics has been used in some other studies here. Okay, so maybe there are some other statistical paths through this jungle of deep learning. So there are three things what I want to talk about. Just give you some overview results, then I will go into the details. The first one is we want to characterize a W-shaped testing error in the nearest neighbor algorithm. This is not deep learning, but we want to look at what happens in if we want to do an interpolation in the nearest neighbor. So what we expect to see in the testing error. Okay, this can be viewed as a more precise characterization of double descent phenomenon. The second one is about classification. We know neural network has been applied a lot. Here, if we view it just as a non-parametric classification problem, so if there's somehow some kind of optimality, so that it can support the size of deep learning in classification. The last one is that we want to treat a sparse neural network without using pruning. Pruning is a more classical way of doing that, but it's more time-consuming. It's a two-stage thing. Sometimes you need to do iterative way. And if we just have some work of regularization of SGD, okay, maybe we can include some soft thresholding so that the weight output by this optimization algorithm itself is already sparse. Of course, in that case, we want to guarantee it still predicts well. Okay. Basically, the old stories will become more and more empirical, more closer to the reality, and the theoretical support certainly will be less and less. Okay, but let's see what the statistical can do here. Okay, the first one is about I call it the benefit of interpolation. Basically, interpolation is very simple. It's also called overfitting. In that case, the training error is 0. Okay. Here, everybody know, right, from classical statistics book or machine learning books that if we want to do a classification, you definitely don't want to do something like that, right? This is a decision boundary that gives you the classification rate of 0, and for regression, you don't want to have this very jumpy function. Although training error is 0, but testing we know is not that good. Okay, so basically it's such that you should avoid overfitting, right? Otherwise, the testing error will go up. Okay, within I call this as maybe a classical regime. And our result here is some other more general double descent phenomenon. This can be has been empirically observed in some neural networks and has been theoretically studied in some regression functions. Okay, there are quite a few studies, and here our results can be just summarized using one plot here. Okay, the left part is the classical regime. You can find it in any textbook to tell you. This one is only for nearest neighbor. Okay, and here is something we discover. It's called overfitting or interpolation regime. For dimension, it's for arbitrary dimension. This plot is only for dimension 2. Okay, so gamma is actually the level of interpolation. As gamma grows, that means you have more and more interpolation. Okay, this you will observe. Then we can this is a theoretical curve. We can notice this go down first and then go up. Okay, up to gamma smaller than gamma d. Okay, if gamma goes to infinity, this becomes just one nearest neighbor. We know one nearest neighbor is just the interpolation, right? Okay, we call this region as the interpolated nearest neighbor. So our contribution is to characterize this curve as a function of gamma. Okay.
Sorry, what is that curve?
This curve is a testing arrow. Okay, y-axis. Yeah.
Which axis?
The nearest neighbor.
No,
For fixed case here.
Okay. Why did it say 1 here? Yeah, what's gamma, sorry?
Gamma is the level of interpolation. I will define next slide. Yeah.
Oh, okay.
Yeah. Here is just you will see this again by the end of the story. I just give you some very vague impression. So you will see very precise definition here. Okay. We care about k nearest neighbor. People know that can be used for regression or classification, depending on y here is discrete or continuous. So our result also holds in both cases. Okay, you have a training data x, y, and x can be a d-dimensional feature. And arrow is just mean zero bounded variance, very standard setup. And basically the nearest neighbor tell you, okay, why I want to do prediction, you have a new test data, right? I just calculate the weighted average about the training data. Okay, wi is the weight, y is the training data. Okay, and how do you find out what kind of training data to use? You just count the closest case to your new coming testing data. Okay, by Euclidean distance here, and your weight summation is 1. And if you want to do classification, you just compare 8 hat by 1/2, and nkx just denote the k nearest neighbor. Okay, just a very standard thing. And what's the interpolation scheme? Remember, our goal here is that we want to make the training error as 0. Okay, how can we make that happen? There are many ways of doing that. Okay, but basic idea is that we want to introduce something called interpolation function phi. And here, this is divided by this one is simply to make the scale between 0 and 1, right? Because this is the largest one, because everything within k distance will be smaller than that. So just make this a function between the support is between 0 and 1. Okay, that's a scaling. This is just a scaling to make the weight summation is 1. Okay, here is that. You can imagine that if I allow x phi at the point x is 0 is positive infinite, you have interpolation like this. Okay, you just plug in 8 hat of x1, okay, into here. This is x1, right? And then I is 1, right? So if, in other words, this argument is 0, then this is a positive infinite, so that w1 is 1, right? That's how you enforce interpolation. Okay, of course, here how fast the phi will diverge to infinity really matters. That tells you different levels of interpolation. Okay? This is one. Okay, here I just want to show you there are different ways of designing the interpolation function, how fast it diverges to infinity. So here I have 3 choices of a phi function, interpolation function. One is 1 minus log t, 1 over t, 1 over root of t. Okay? You see, this curve approach to 0 is diverge at different rates, right? You see the right curve will diverge to infinity faster, the green one will be slower, right? So this is corresponds to the regression case, okay, the nearest neighbor regression. So if you choose this one, 1 over t, the green curve, so that interpolation is slow, So you just pass into this point in the. It says the slower green one will be slower to infinity. Oh, sorry, you are right. It's faster. Yeah, this is yeah. Given the same t, the green one will be larger. Yeah. Yeah, you are right. So, yeah. So I use 3 different curves to tell you it has different divergence rate, and this will correspond to the way you interpolate this point. Okay, because once you interpolate this point, the training error will be 0. And here is the high level idea is that if I do an interpolation right, I choose the right interpolation function, the change of matter will be 0. So you still have this minimax optimality. Okay, because for example, I just draw a very basic plot. Say for example, traditionally you do a regression. I use a regression as an example. Okay. For example, that's traditionally how you do it, right? You got such a curve. Of course, it should be piecewise. Okay, for nearest neighbor. But let me make it simple like this way. And how to make it interpolated? I just modify here. Like this curve pass here, right? So we have to use some color. Modify here. And modify here locally. Modify here. Modify here. Modify here, right? And if this modification is so small, the induced matter will be 0. So the passing error will be affected very minimal, right? So how you define this interpolation function matters. All right? And then let me show you, okay, here is the one I just saw. Okay, this is the 2 curve you want to estimate, smiling curve. And actually you have different options. Why is this green one is just a k nearest neighbor estimation, a regression estimation for the smiling curve. And you have 2 different interpolated curve. One is the blue, another the pink, right? So they actually, both this blue and the pink curve actually pass through the training data, so the training error is 0, right? But you can tell that the way it passes through the training data is different, right? Okay, so that tells you you should choose the interpolation function carefully. This is our main theory, right? Okay, I simplify a little bit. I choose the interpolation function as t to the power of negative gamma. That's how much you do interpolation. The level of interpolation is encoded by the value of gamma. Our theory only holds for the case gamma between 0 and d over 3. D is the dimension of the feature. Okay? And we just make some very basic assumption on how smooth the underlying regression function is, how smooth the density x is, and support of x compact. This can be relaxed to Gaussian. So given this one, if I choose the case, we know this case is the optimal twice of k, okay, for nearest neighbor case. And we have the following result. Is this a full regression? It's a mean square error. This is the mean square error for the k and the optimal twice of k. And this is the mean square error of the interpolated k up to the gamma. Okay, so this will be a very nice form. This constant is actually independent of your underlying function. There's nothing, only gamma and d. Okay, d is the feature dimension, gamma is the interpolation level. So it's a very elegantly to characterize how much you compare the mean square of interpolation with the uninterpolated k. That's the best. Okay, so basically we can use this very simple function to characterize the benefit or loss. Okay, we have to see how it goes, right? And also applies to the classification as well. You got the same constant. The interesting part is that this is there's no distribution involved. Yeah.
What is interpolation with T and what's Kn?
What's K?
No, Kn. The denominator of Kn.
Okay, just the optimal K. Just the uninterpolated one. Just you use the 1 over K, the weight will be 1 over K. Yeah, the weight is 1 over K. Yeah, just use the K, K nearest neighbor. Right, for 1 over K. It's the one people use, every day, okay. Okay, so, once we have C gamma D, right, we are able to fix the D. In this case, D is 2. We can write down this curve. We find out something very interesting. First, S gamma is 0. Here is the optimal Kn. So goes to become positive. Because once this becomes positive, then this goes to infinity as t is 0, right? What?
Why do you call it optimum again?
Because I choose the cases as optimal order.
In what sense is this optimum?
Oh, it's in the minimax sense. Yeah.
So for regression, it dimension is optimistic case.
Yes, the rate optimality. Yeah, rate is optimal. Yeah. Okay. And once we have a C gamma D, it's very easy to to numerically plot that, right? So you got this one. As once gamma is positive, then actually the testing errors go down rather than as what people think go up. Okay, it go down. Okay, then go up again. So that's what I call as a W shape. Of course, our theory so far only holds for gamma between 0 and 2 d over 3. And this gamma d tell you that if your interpolation level is at gamma d, then it will be the same as the uninterpolated one. Okay, and this is one just gamma is a representation point. Okay, we don't have a theory to what happens if gamma larger than d over 3. But, yeah. For the left, okay, for this point, gamma is 0, but here is, I keep it a little bit vague, okay, because I call this a model complexity. Maybe this can be viewed as the twice of k, or the weight for each neighborhood. Okay, here I'm not so precise. This does not mean gamma is negative, okay. Gamma is, basically I put the two plots together, okay. This is the plot, the right one is what we got, and this one I call it as a classical regime, people know, okay.
Classical regime of what?
Of the nearest neighbor, how the testing error will change. It should be have this bias variance trade-off as well. Okay. So here is I'm a little bit vague. That's I can.
What's
Yeah.
the difference between overfitting and different words?
The overfitting means the training error is 0. I call this the overfitting interpretation. Classical means the training error is not 0. We should balance the training and test. Okay, that's what people did.
I see.
Yeah.
That is what.
Yeah, that's the classical. People know it's the one I showed you in the beginning is textbook one, right? So the idea is that this one I just put there. Yeah, to my last. So just for comparison. Okay. Okay. This actually I haven't finished this problem because there are many questions. To a lot more to do actually. Yeah. Oh, this is good. I can give this. Okay, just look at here. This is one thing I didn't say because I hear too much. This is called the optimal weight use neighbor. Okay, that means this one and this one they share the same minimax rate. But if you are even more careful in choosing the weight, not 1 over k, it's a different weight according to the distance to the test data. You got something called the optimal weight. This one has a smaller multiplicative constant. Okay, this is the best one. So you see this point is the lowest one. Okay, it's lower than this one. Basically, what we are doing is that I use interpolation to choose the best weight. Okay, here they have a mathematical formula, but here I use a interpolation weight. That's why. I mean, what I'm saying is that this one is better, not because the rate is better. They share the same rate optimality, but the multiplicative constant is better. That's how the C gamma D come from. You see, the rate will cancel out. It has the best rate. This also has the best rate, but this multiplicative constant is smaller than it. Okay, but this should be very subtle analysis on how you do interpolation. Okay? Yeah. Yes, yeah, that's more than this one. Yeah. Yeah. This is the formula. Yeah. That if you fix the D is 2, you can see that one gamma is between 0 and the gamma D, something gamma D. So implicitly defined, this one will be smaller than 1. Yeah, you can do this easily. Yeah. Okay, yeah, just trust me here. If the gamma is between 0 and gamma D, this curve is always below than this one. Basically means C gamma D is smaller than 1. Okay.
And in principle, you can optimize for given speed, optimize for gamma, right?
Yeah, I can choose this gamma as the optimal one. Yeah, I can do that. Yeah, because it has a very explicit form. Okay, but this is still very far from neural network. It's very easy to analyze the nearest neighbor one. Okay, but so as I said, the second story will be more close to reality. Okay, there are a lot more to do because there are other forms of double descendant phenomenon. If you read some Interpol paper, they do simulation. They have something like that, and there's another thing. Double descent may not be so revolutionary because this is still reflects the way how you define model complexity, right? Here I use the gamma to tell that's the interpolation level. I use L2, right? Mean square error is L2, yeah.
What is model complexity?
Okay, here I just use the gamma as a measure to represent how much it interpolates. But if I use something different, or I don't use the mean square error, I use a super different, super norm. Mean square error is L2 norm, right? I can use a super norm. I try to use a super norm, you will not get this double descent. Okay? It's up to a lot of things, double descent, right? Mean square error, use L2 norm. One descent nearest neighbor, how you define distance? I use L2. Maybe I can use LQ. You will have very different phenomena. So this double descent may be just some artifact of the measure you use. Okay, yeah? Yeah. This one, yeah. Oh, you have to assume this, yeah. It's some smoothness of the underlying function, H. I didn't specify here. There are some smoothness, but they are slightly.
But then you don't think after about the C gamma uniformly for all functions that's flat.
It is, yeah. It is, yeah. It is. Yeah, that's why I like this result. It's a distribution rate result.
I think you said it's a min-max.
Min-max itself is a uniform, right, over this. Right, yeah. But here we got this.
It's probably not true for all functions.
Yeah, I include some conditions. Not all functions.
No. This limit cannot work for all functions.
Yeah, and this, if you talk about functions as 8 or something else.
It must be a minimax thing. It's not that.
Yeah, there's a set of 8. Yes, there's a set of 8, which I should specify.
Right. So what this shows is that everything is more that, and there is a function in that class where it's the role.
Right, I can find out that estimator which can and which this holds here uniform in some.
No, but just to clarify, median of right arrow is just that it's a minimax.
It's a mean square error. It doesn't need to be a minimax bound, but it's a mean square error. Yeah. We give a exact formula, not a upper lower bound. Mean square error here I can write exactly equal to some constant times the rate. Okay, that's different. It's more precise than the usual minimax. You have upper bound, lower bound, right? You have there's a gap here. There's a constant you don't know, right? But here we specify the constant. Okay, that's how this C gamma can come from. Right, I mean,
because something is a constant, at any given point, averaging anything in the neighbor is the optimal thing.
right, I mean,
And any interpolated thing in the neighbor will be something.
for the constant function, you should, some other cases it will be excluded by some regularity condition.
Why? The constant function is as smooth as you can get.
Yeah, maybe I should specify this. I also have noise condition because it's so that you can do a right classification. Okay, but let's talk about this offline. I do have some. This online archive you can find out actually. Okay. Okay. So next one is about the optimal classification. Of course, I have to define what optimality is here. And here we have enough motivation to study that. Okay. And this is Interpol result. Probably everybody know that once we have this introduction of CNN, that actually image classification has been dominated by deep learning methods. And how can we explain the empirical success from a statistical optimality perspective? Okay, here I define something called the teacher-student optimality. Okay, basically this is a type of statistical optimality because the L here is a loss, F hat, F star. Here, F hat is from some student network, Fn, and F star from Fn star, I use this to denote so-called teacher network. Okay, this is different from minimax. It looks similar because usually minimax I assume F star from whatever smooth function. Okay, that's more commonly.
Wait, so
yeah.
This is loss on empirical data produced by Fn? What this L is loss?
Yeah, this can be expectation of iPad so that you can expect off the random.
No, I'm just trying to understand the notation. What is F?
N is a sample size.
L.
L is a loss function. 0, 1 loss. I will define what L is like for classification, 0, 1 loss. Yeah. I will define next slide. Yeah, the here is just give you a general concept that I want to introduce this optimality within the teacher-student framework. This F star is where you generate your data from a teacher network, and I want to learn from a slightly larger Fn, which is a student network, and you certainly want to know the relation between Fn star and Fn. That's something I'm going to talk about. Okay, and I want to get this rate is dimension independent. There are so many minimax results to tell you that this is some function of dimension, so you have to need exponentially many samples to do a good classification. That's not the case for deep learning, right? Certainly, we want some bump without dimension. So that's our first goal. I want to find out a sharp and dimension-independent teacher-student bond for neural network classification. Second thing is that I want to make a connection with the very classical non-parametric classification literature. So why there is a dimension-dependent bond in classical literature, but why I don't have that dimension-dependent bond. Okay, I want to make connection. All right, here it may answer some deep questions, so to know how it looks like. Okay, we have feature X in the D-dimensional feature. We just do binary case. Okay, positive 1, negative 1, and certainly given 0, 1 loss, we can define the Bayesian classifier. Okay, C star, which is not obtainable. But we can estimate C star by minimizing the integral loss. Here is a 0, 1 loss, right? And this you can use F, maybe it's better to be consistent notation, F of Xi. And in practice, I mean, this is not practical. We have to use surrogate loss. I will talk about this as well. But here, let's just stick to 0, 1 loss. Okay, this is a generic definition and not practically useful, but may deliver some insight. Okay. Then I will talk about surrogate loss. Okay.
I'm confused. So in your previous slide, you have L of F hat and star. That's what.
Right. This is so the Y view from the F star. Okay. This is F hat. Yes. Yeah. You can think that way. Yeah. Of some underlying function to generate the training state one. Okay. Yeah. So yeah, I probably should use the same notation. Sorry. So. Okay. Okay, here is I just defined some notation. Everybody know about that for deep neuron.
Usually that's not the definition of, I mean, in teacher training you sort of imagine that some input from standard distribution are fed to another.
Yeah, I will talk about that in the theorem. I will define how we define the F there, how that can make connection to the teacher network there. It's about decision boundary. It's a classification boundary. That part is from, it's a P minus Q from the teacher network. I will come to that one. Okay. Okay, just next slide. Okay. So very good questions. Deep neural network can be defined recursively like this way. Sigma is just apply the element Y. Okay. And it's a very generic definition. W is a weight matrix. And actually, the activation function we focus on in the whole talk is just the loop. Okay. And actually, some nice properties we will use for the loop, actually, for the theory. Okay, we define the student network Fn as a loop family with Ln is the layer, maximum width is a big N, number of non-zero weights is Sn, and the maximum value of this non-zero weight is bounded by Bn. Okay, just some notation, and as you can imagine, all these things will be used to define the capacity of the student network. And the point is that how you control the size of teacher and the student. Okay.
Now, number of non-zero weights, that's just like number of edges, that it's not a complete number, or...
Yeah, it doesn't need to be fully connected. It can be sparsely connected.
That's all you mean?
Yes, yes.
Number of edges.
Yes, number of edges. Yes, yeah, it doesn't need to be like fully connected. Yeah. So for this teacher-student optimality, I call it optimality because here is you have alpha and the lower bound. Okay. You say there's no dimension here, 2 over 3, but let's look at it from the beginning. So I assume two density, and y is 1, is -1, right? The two density should be distinguishable, right? Otherwise, you are not able to do classification. So the first one say the case they are not distinguishable. This is actually the -0. Okay. Second one is that this is the teacher part. So the p minus q, their difference. Okay, can be modeled. This is certainly an assumption. Can be modeled by the loop family with the following notation and the assumption. Basically, you should require the depth of the teacher one smaller than the depth of the student. But the upper bound is always big O of log n. And this is the relation between the teacher and student. Okay, and the Bn is the bounded value for the non-zero weight.
So you said the sparsity, and you're saying that the sparsity of the network is again?
I mean, upper bound is like that. So, yeah. So there's a more general condition that, so the Dn can be either sparsely or fully connected. Okay. I have a general condition. This is just a special case of the general condition. Yeah. Okay, this is not the over parameterized. Okay. This is log n, right? So
that's fine, but I'm just wondering if your layer is growing, your layer is growing like n, right? That's
yeah, that's the width. Yeah, that's the width. The line is the width. It's grow as n. Yeah. Okay, but this also applies to this. I only have an upper bound result, so this certainly applies to shallow one, not to double question.
No, let's assume that's true or that's three, right? I'm just simulating. Just wondering what does it mean about the sparsity if I have that n, my width is n, or even root n, but my sparsity is only log n.
Right, but here that comes from how many connected edges. Yeah, this is irrelevant to the magnitude. Right. So this
Right, but that basically means your network dependent on only like log n.
What does that mean, sparsity?
Right, basically, it's the weight of the, it's double. It's talking about the double. It's how many of the elements in double than 0.
Wait, for a row or a total?
A total. Total. Not the layer.
But that's the chance question. You have n rows, and log n are not zero.
Okay, I see your point. Okay. Any is a sample. Yeah.
Capital N is the size of the matrix, the dimension, right? And if I have a capital N by capital N matrix,
Yeah, I think this. I should go back to double check. I think this probably per layer it should be logged. Otherwise, the conflict with this. But that's that's the problem. I mean, when we calculate the entropy number, the bound is a bit loose, so we cannot allow the network to grow too fast. That's technical reason. I believe this may be sharpened, but can this be sharpened to the polynomial n to the power of 1 half? Something we are not sure. It's still about the technical. We use the entropy number, and that could be to loose the bound. Yeah. Okay. So here is may not be the best result, but this whole certainly. And these conditions, we got this teacher-student bound as n to the power of -2 over 3. Okay, so there's no more dimension here, and the evidence star is the p minus q should satisfy these two conditions. Okay. So this can be sparsely or fully connected. This is certainly a very strong condition. I agree. Yeah. Okay, so let me try to make connection with the non-parametric classification result. Yeah.
Can you say why you think the theorem is rising or
Okay. Yeah, why there's no dimension?
yes?
Okay, I think the reason is that it's a kind of translate from a non-parametric form into a parametric form. Okay.
But in this setup, you assume you generate the data from a feature. The feature was a parametric model, right? So
It's a growing dimension. It's still we can view as a parametric model, so the dimension here can somehow disappear from the power. Yeah. If we assume you will see the dimension in next slide. If we do a traditional assumption, you will see dimension. Okay? Okay. So I think the short answer is I turn a non-parametric form to a parametric one. Okay? And, here is the usual assumption for classification. Maybe some of you know about it. They assume this is a G set. It's called smooth boundary condition. It has a union or intersection of R smooth hypersurface. They have the so-called set of low noise condition. So this the alpha and the kappa will control this rate. Okay, this is the minimax rate for the non-parametric classification. Okay, there's nothing about neural network. You can see the alpha times k plus 1, and the more important thing, this term is d minus 1. Okay, dimension show up here. Okay, alpha is how smooth the boundary is. Okay, it's very technical. I have backup slides if you want to see some R smooth the horizon function to define that. Okay, this is a practical result. Okay, it's different from ours. So how I make a connection? Okay, I just copy paste the minimax lower bound. Okay, and actually we know a larger value of alpha. So more smooth the boundary is actually the classification. Okay, a larger value of alpha leads to a smaller space, right? The smoother the space is smaller. Okay, and the Dn function space is smaller than any alpha, so I can assume that alpha goes to infinity. If we take alpha goes to infinity here, this power becomes negative gamma plus 1 over gamma plus 2. But there's no more d here. Okay, then I use the rule, actually the Dn piecewise linear, it implies the gamma here becomes 1, it is reduced to 2 over 3. Okay, why I say turn the non-parametric form into parametric, because parametric means you have infinite smooth case, so alpha goes to infinity. And the kappa is 1 because I use the loop, so it becomes 2 over 3. Okay, still recover from the classical result. Okay, that's why I said you go from non-parametric to parametric. That's my impression so far. Okay, and actually this can be improved to 1 over n rate. If P and Q have a disjoint support, that means kappa can take infinite. So this is 1 becomes 1 if kappa is infinite. Okay. Okay, there's some recent results. People still try to use the traditional minimax analysis to analyze the neural network classifier. They got this rate. This is not optimal because there is case kappa plus 1, and here is the kappa, right? It doesn't match with the classical minimax lower bound. Maybe because they have used the surrogate loss rather than 0-1 loss. And actually, this is not a good result because we have dimension here, right? But somehow we can manage to reduce this dimension d to something called much smaller effective dimension if we imposing some convolutional structure of smooth function that defines the decision boundary. There are some technical details I put to the end of the talk. So, but the idea is that we can further reduce the result, this dimension d to the d star, which can be much smaller than d. Okay? What's the key problem so far for all this technical optimality results is that we only prove the existence of some technical optimal results. No matter we are talking about minimax optimal or the teacher-student optimality I just introduced, then we only prove there exists such a optimal estimator or optimal classifier, but we don't know how to get it efficiently. Okay, it's more like the worst the case, what it happens, what it looks like. Okay, because you put mics over all the teacher network, you don't know which one you draw actually. It still provides some algorithm independent results. Okay, because did I mention that I like this result from different perspective because this is an algorithmic independent result. No, probably somewhere else, maybe later time. Okay, anyway, this is not relevant to the algorithm. What do you use? Okay, it's n to the power of -2 over 3.
Why is -2/3 the minimax rate here? Because
It is not minimax, it's just some.
okay. Because you should be able to get 1/n when you have margin. The optimistic.
I use the rule we got this kappa is 1. It's basically we calculate the entropy bound to get this one. And the high level answer is that you go back to the classical framework, you choose the kappa is 1 for that.
Because using optimistic Rademacher complexity, you can get 1/n when you have margin.
Okay, I don't know about that. Yeah. But that can be translated to the same conclusion. Because here I'm talking about the log, so I'm not sure how this margin result can carry over.
I mean, I think your assumption on P and Q being separate is basically margin, and then.
Yeah, but we characterize in different ways. Yeah.
Yeah, maybe. Yeah.
Yeah, that's maybe we have a stronger assumption. Maybe I don't know. I didn't see the result you talk about. Yeah.
This log n thing is very mysterious. I mean, you cannot.
Log n.
This just seems wrong because I mean, it is minimax or something that it has to work for all.
There's a log n I didn't write. Maybe you should. There's a tutor
No,
log.
SN stuff.
Oh, yeah. Here. This may be the technical thing. Maybe not be the entropy to lose. Yeah.
It's saying basically that your function is going to depend on only log n.
Right.
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 So it's really a log n. It's a function log n. Not an n.
No, the input dimension can be d. Input dimension can be d. Yeah.
Oh wait, n is what?
N is the sample size. Yeah. So
Oh,
input
I see.
dimension.
So you're assuming number of samples is exponential. The size.
I mean, from this result, I don't need to. Yeah, because there's no d here.
Yeah. So I see. So the width of the network is.
Input dimension.
Then what is happening?
Capital N is the maybe you should look at it. The maximum width. Okay. Maximum width.
So the input here is B, and then it becomes that.
Yes. After you yeah.
So I just call that B again, and then the number of non-zero weights is logarithmic. That's the number of samples. But of course, the number of non-zero weights must be D at least because it has to depend on the size.
Yeah, it's not a low dimensional manifold. Yes. Yeah.
I mean, it has to depend on that. So therefore, the number of samples is exponential.
I'm not sure about that.
That's what it is. The weight is logarithmic number of samples. So therefore, the
This a weight. This is yeah. Yeah. I'm not sure why this has to be used because you have to see. Okay, yeah, and in the beginning, yeah.
Yeah, in the very first layer.
Yeah, in the first layer, yeah.
And so, what you're saying is number of samples.
Okay, I see what you mean. Okay, you want to match this log with the d, right? So that every dimension can be represented for the for that part. Okay.
First layer, right?
Yeah, at this first layer, yeah.
And so.
Yeah, there is motivation to improve that, but yeah, yeah, it makes.
You're going to be minimax for all functions. You're going to need exponential and d-dimension.
Maybe the case that we move the dimension dependence from here to here, but I need to double check because we have more general condition. Maybe I can strengthen here. This become log n, for example, and then here becomes polynomial. I'm not sure. Yeah, this just we have, as I said, we have more general condition here, which we just pick one that is easy to present because in total just a constant number. A number of parameters. Maybe we can distribute it in different ways. Yeah. But I will get back to you. I will go back to check more general. We have more general than this I presented. Maybe in that case it's a polynomial. Yeah. Yeah, we didn't think very hard on that, how to find the most representable result. Okay. Okay. This is more empirical result. Okay. The training of sparse neural network. We need to get some motivation, right? So we have some slicing of over-parameterization, right? It can help optimization-wise and also can accelerate, say, for example, say, that can be used to accelerate that cannot be achieved by regularization and momentum, and we also prefer larger network. It can be more representable, right? So it even has some lower bound result in approximation theory, right? So the width has to large, cannot be represented if the width is smaller than in 2 dimensions. Okay, basically you see, okay, we prefer over-parameterized, but on the other hand, this over-parameterized or dense neural network has this storage problem, okay? And also computation constraint, right? And also maybe this may not be true universally, but sometimes maybe less robustness to adversarial noises. The sparse neural network may avoid some of these issues. And here we have 2 goals. One, we want to speed up training, right? Because we can ignore the zero weights and zero gradients, and we want to preserve accuracy, right? If you do sparsity too much, maybe the over-parameterization will disappear. If it disappears, you may have optimization of the generalization issues, which I will show you in a empirical talk. Okay, here is basically about to answer this best paper question, so how to find a winning ticket. In this paper, they provide this 2-stage thing, right? I run a fully connected network. I do pruning, called magnitude pruning. They can even do it iteratively, retraining, repruning, retraining, repruning, okay? And basically, what I like is that they have this conjecture saying there exists a sub-network in a fully neural network with comparable test accuracy to the original one if we train just in a similar number of iterations. Such a network can be found by magnitude pruning they propose, and it has, of course, in this case, you have to retrain it. Because first you find out which is non-zero, which is a zero, then you have to train again the non-zero ones using the same initializer. Okay, basically the winning ticket means 2 things. You use the structure, the sub-network, and also the same initializer. But here, they have very nice results. They only have use 10 to 20% size of the original fully connected network. But there are 2 issues here. One is that there's no rule to determine the P, right? P is how much you want to prune, okay? The P percent. Second is how retraining is time consuming. You don't want to do that. You want to do it in one shot, okay? Here is the goal we want to achieve, okay? What's a good algorithm? It has the following standards. One, it does not require too many tuning parameters, unless you have some theoretical guideline. Here is a statistical guideline. Say what the tuning parameter you should choose, or at least you can give a range. You don't want to test and trial and error things, right? For example, in this graduate. Yeah, it's a hyperparameter. All this learning rate thing. Yeah. Okay, for example, there's a counterexample saying that for the graduate magnitude tuning, the pruning, they actually have a sparse rate scheduling thing. They have to be very careful there. And you want to have this comparable computational cost to SVD, right? For example, in this paper, they have 2 times memory, 3 times training SVD. That's not ideal. Okay, it's called variational dropout. And it should be algorithmic adapted. See, I have different algorithms, then the hyperparameter should be adapted to that. I shouldn't use the same hyperparameter. Okay, and I have some special guideline in tuning or choosing this hyperparameter. So here we propose something we recently studied called the generalization of regularized dual averaging. I'm not sure how many of you know about regularized dual averaging. It's just I want to output some sparse estimator by introducing some kind of regularization. Okay, but here we
regression.
this can be regression, yeah. It can be something else, yeah.
It's a general algorithm from
general SVD is basically one step beyond SVD, yeah.
So what's the form?
Because it can be written as a dual form, yeah.
Which
okay, in the dual form it actually accumulates a gradient. I will show you. Okay, let me show this just the empirical result. This is a training error. Okay, it's too small. Let me read it for you. This is from ImageNet. The model is RateNet 50. learning rate is 0.1, batch size is 256, and it's still too small. This is a training error, and we have several different curves. The first one is the vanilla SCD. I don't have a momentum or weight decay, and the rest is what we propose, called the generalized RDA. C and mu is the hyperparameter. I just took different C and mu here to see how it changed the testing error or training error. C is something I will introduce later, so maybe easy for you to see the formula. Okay. I have something called a tuning function. It's a C, there's a mu here. I will come back to it. It's the way that we design the optimization. Okay. G is the tuning function, so how much you tune this L1 tunization. Okay.
How much you think that?
Yeah, how much? This is a very subtle thing. You have to study the continuous time approximation to pin down the form of G. Okay. Let's go back to Interpol. Okay, if you look at this, the training error, okay, and this testing one, this sparsity means, for example, that means 90% of weights are 0, okay? You only use 10% of the original size, okay? For example, of course, here, I mean, SCD is not sparse. You just compare a different GRDA. You will see they have some difference after 140 epoch. And for testing error, we didn't train very carefully because it's ImageNet. We don't have enough resources to do that. And we have achieved, say, maybe 71, 72% at best. And this is SCD because I didn't use a momentum or weight decay, so it's even worse than the regularized version. And the best I just checked yesterday, is 77% for the RIS9 if you use the SCD plus the momentum and all those training techniques. Okay, but here the point is that we can still achieve comparable testing accuracy to the SCD approach. And for the particular, you want to pay attention to the right line, is in which the training accuracy is approximately the testing accuracy, and it has the highest sparsity. Maybe it tells you the sparsity is kind of like help you to balance the testing and the training. This is heuristic, just observation. Okay. Okay, so here are some implementation details, and my students run this, so I don't necessarily, I may not know very, very detailed thing, but basically they actually use the some official implementation in GitHub, and then they use the vanilla SCD, and also basically they just use the default common, okay, and the fixed learning rate 0.1. They use the same initialization for better comparison, and that's all we have to run to P100. We run this, so it took us quite some time to do this in ImageNet. Top one, yeah. Top one only, yeah. That's why only 77, yeah. Okay. Here, there are many other ways for doing this sparse neural network, right? I'm just comparing with them. Or too small, okay. This the cross is our method, and here is top one accuracy, and here the x-axis is the sparsity. So we care about here, right? It should be highly sparse. Of course, for most method, if you like 99% are 0, then certainly the accuracy is very bad. So probably we should look at this block. Here, if you this is zoom in, you will see something like that. When we are near to the high sparsity range, we are close to the so-called magnitude pruning. Random tuning is the yellow one. It's very bad, as you can tell. The top one accuracy is very bad. But if we compare with the variational dropout or the magnitude pruning, we are close to them, especially for the high sparsity region. Okay.
So the yellow one, the
random one is very bad.
and then the blue one.
The blue one is the magnitude pruning, which I introduced.
The red one,
the cross one is our method, and this one is variational dropout. Okay.
Oh, the one.
There are 4 different.
The variational seems to do the best, but you said it has high space and constant one.
It's 35% over. Yeah. But when we come to this region, we are comparable. Okay, but again, they use more memory, and we are doing one short thing. Okay. So, okay, here we just say our method may reach a higher accuracy if we use a fine-tuned learning rate schedule. We didn't actually. We don't have enough resources to do that. And the increased sparsity actually. One thing I want to point out If you keep increasing the sparsity, it turns over parameterization. From after here, you actually have a less parameter than sample size, okay? Then you will turn the over parameterization to under parameterization from here, okay? You have so few parameters. In this case, the test accuracy is no longer good. So it tells you that sparsity is something very subtle. You shouldn't be too sparse, okay? And we are trying to develop some theory for that. I mean, how sparse it should be, okay? Now here is giving us some empirical result. And GRDA is very easy to implement. Actually, this is the traditional way to use SDD. We just need to change one line in the program. We just change this one, SDD, to GRDA using our package. Then you can do it. Okay? Relatively easy. Okay? Yeah, I know. It's we put things on the GRDA here, and the tuning is relatively easy. Maybe I should say this way. Okay. Yeah. Okay. The time is time-wise is that it's we basically comparable to the SDD, and the memory-wise is okay. Okay, here's give you this some details. Maybe that's something I should put it earlier. Okay. Okay, I just give a special case of GRDA. You have a more general form. I call it the L1 GRDA because this, I use the L1 norm to penalize the W, which is the weight and in the neural network. And this G gamma is actually, you can view this as a kind of dual form. Okay, can be written as a two-way. Okay, this is a dual form. And this is actually accumulator of the gradients. And the Gn gamma is the key thing, how regressive you should penalize those weights, right? If this is super big, if G is super big, then most W is 0. We know that from the empirical result, it's not good. And this is double square is more stabilized purpose, okay, stabilization. And I can rewrite it. This is probably more clear. This it's not easy. This is basically you are doing a soft thresholding of the gradient, and the way you do it is in this form. If if a G gamma is too big, then we can keep that minus the G. Okay, otherwise it's a 0. Okay, so this so as you can tell, the G, the threshold in G is really matters. That depends on how aggressive you want your neural network to be sparse. Okay, so everything will reduce to the twice of G. Okay, basically we have two additional steps beyond SDD. One is gradient accumulation, and another soft threshold. Okay, how to choose the G and gamma? We have to use some statistical theory to tell us here. It has this formula C, it's constant, times gamma is the learning rate to the power of half, times gamma n is the sample size to the power of nu. There are two parts, I will interpret them separately. Okay, first the gamma is the learning rate, the mu and the C are something the tuning or hyperparameter. In general, larger values of gamma and C leads to higher sparsity. If you go back to see the empirical plot, you will notice that. In linear regression, we can prove that if mu is between 0 and between half and 1, and if C is totally large enough, we can have a support recovery consistent online linear regression if you do that. So that tells you you have to choose the mu is larger than 1/2 at least. That's what we use actually. That's what I call it as a statistical guideline. Okay. So why it has this form? It's gamma half is actually scaling that enables some reconvergence results, like central linear theorem. And gamma n to the power of mu is controls how the threshold actually vary over time. And this is our theory doesn't apply to neural networks, apply to online linear regression. And we got something like this. If we set mu is between half and 1, okay, and large enough C, this is a linear regression by the way. And the GRDA as the form I show you, for the inactive W, it actually goes to 0 because learning rate goes to 0. You have a support recovery result. And if it's not 0, we can show this converts to standard norm. Okay, we have some linear results can enable you to do some inferences if you want. Okay. And actually, in SDD, actually, people know that for the inactive variable, it goes to 0. I mean, slower because it's a big OP. If we penalize that, it becomes from big OP to small OP. So it goes to 0 faster if you penalize it. And by setting mu is larger than half here, we are able to denoise not only the active, but also the inactive variables and the inactive weight are thresholded to 0. Okay, there are some theories behind, but again, this is for the for linear regression, but we use mu is 0.501, something that works fairly good. And this is the optimizer, and we basically we have something. Okay, what to do next? Okay, we should fine-tune the GRDA. We haven't added momentum or adjust the C value across layers, and we should test on more different neural network structure, and we should develop the theory of the GRDA for the neural network, not only linear regression. So we want to answer the two questions. Firstly, so will the induced sparsity improve generalization ability? We don't know this yet. So far, it seems not. Okay. Secondly, so what's the largest sparsity that can still guarantee good generalization? It's more like a lower bound than upper bound for sparsity, right? You want to know, okay, you want to have the most memory efficient sparse neural network, but its generalization is as good as the fully connected one. Okay.